This is experiment 14, chemical equilibrium. We've alluded to this before in several instances, but not addressed it directly. But in reality, all reactions go forward and backward. We've talked about this in the context of weak acids and weak bases. Let's look at the example of hydrofluoric acid. We're drawing this double arrow here to show that for every HF molecule that breaks up into H plus and F minus, a pair of H plus and F minus are coming together to form an HF molecule. And so to define the state of equilibrium, we can say that the rate of the forward reaction, the rate of this HF dissociating, equals the rate of the reverse reaction. The rate of these H's and F's coming together. So the equilibrium constant is a value that describes which side of the equation is favored, whether there are more products present at equilibrium or are there more reactants present at equilibrium. So the equation for that is, call it KEQ, equilibrium constant, and that's equal to the concentration of products over the concentration of reactants. In case we haven't gone over this before, when you put something in brackets like that, it means concentration. And up here, as an exponent, as a power, we are going to put the coefficient, the stoichiometric coefficient from the reaction. Let's look at an example. Got some magnesium iodide in the aqueous form, but we're going to pretend that these ions are still associated and that they're in equilibrium with the dissociated ions. So we've got magnesium 2 plus and 2 I minuses. So my equilibrium equation is going to look like this. KEQ equals my concentration of Mg2 plus times my concentration of I minus, but my I minus is going to be squared, okay, because of this coefficient right here. Then that will be over the concentration of magnesium iodide. Right, so we're dividing products by reactants. So if there are more products in solution, we're going to have a really big number because you'll have a large numerator and a small denominator. But if you have more reactants, then your KEQ is going to be really small. So if KEQ is greater than 1, then the products are favored. There are more products present. And if KEQ is less than 1, did I say less than 1 up here? I meant greater than 1. Less than 1 down here, then reactants are favored. So in the instance of a weak acid or a weak base, then the reactants are almost always going to be favored. The reactants. You're going to have a lot of HF and not very much H plus or F minus, just in general. So one thing to note here is that there are no solids or liquids. Everything here is aqueous. Only aqueous or gaseous species are included. So if water is one of your products, liquid water, you're not going to include that in your equilibrium equation. So that's what it looks like at equilibrium, or that describes equilibrium. But what happens if we disrupt the equilibrium? That is Le Chatelier's principle. And so we can take a system that's in equilibrium and do something to it to stress it out. So when an equilibrium is stressed, it will compensate somehow to reestablish the equilibrium. And I need to go off on a tangent about this for a second and tell you about a sandwich shop that exists next to my parents' house. I grew up next to it, about 5 doors down from it, and we grew up near a military base, and this sandwich shop was the only establishment within walking distance of the military base. And if any of you have ever been in the military, or you know someone who's been in the military, you know that the food that they serve on base is absolutely terrible. So you can bet that every single day that sandwich shop was packed at lunchtime. And so the fire marshal only allows a certain number of people to be in the shop at a time. And so once it fills up, you have to have somebody at the door checking people in, letting one person in for every one person that comes out. One in, one out at the same time. The system is in equilibrium. And at some point during this rush, however, the line gets so backed up outside that somebody opens a back dining room. And that allows another 10 people to come in. That disrupted the equilibrium a little bit. So for just a moment, 10 people are going to rush in without another person coming out. But then as soon as that's done, we return to equilibrium. One in and one out. We just have a few more people inside the sandwich shop than we did before. So how can we stress out a chemical system? We can do that in 2 ways. The first one is the common ion effect. The common ion effect. So that's when you add something into an equilibrium that's already involved. So if you look back at the equilibrium up here, we have magnesium iodide, we have magnesium 2+, and we have I-. So if I add any one of those species to the system, then it would be the common ion effect. So if I, say, added a little bit more of magnesium iodide, then that would give me more reactants. And so the system is going to compensate by producing more products. It's like ordering more ingredients for food. Once you have more ingredients, you can make more food. So that is pushing the equilibrium forward. And I can do that for the reverse direction too. Say I add sodium iodide. Sodium iodide, if you'll remember your solubility rules, is completely soluble. And so you're going to end up with some sodium floating around being a spectator, but you're adding, the thing that matters is that you're adding iodide. And once you add some iodide, that pushes the equilibrium back towards the reactants. It's like when your kitchen starts to get full, you stop cooking a little bit. And so that will push the equilibrium backwards. So here's the key takeaway for the common ion effect. When you're adding an ion that's involved, you are pushing the equilibrium to the opposite side. So anytime it's the common ion effect, you are pushing the equilibrium to the opposite side. That sentence is so important, I'm going to highlight it. I recommend that you do as well. The other way to stress out a system, unsurprisingly, is called the uncommon ion effect. And so that's when you add a species that's not directly involved, but it affects the equilibrium in another way. So we'll refer back to our original equilibrium example in a second. If I added some sodium nitrate, I'm sorry, that is silver nitrate, not sodium nitrate, silver nitrate. What that's going to do is remove some I- from the equilibrium. And that will pull the equilibrium forward. Don't worry, we'll draw an example in just a second. So silver and iodide, silver iodide is insoluble. It does this reaction. So we've got Ag plus aqueous plus I minus aqueous. And that is in equilibrium with silver iodide solid. Now I'm putting this double arrow because it is technically in equilibrium. Technically the reverse reaction happens, but the equilibrium constant for this reaction is huge. Products are massively favored over reactants. So let's draw our ions in solution at the bottom of the page and see what this looks like. So we have our original equilibrium that we were looking at, our magnesium iodide dissociating into magnesium 2 plus and 2I minus. Let's pretend that that looks like a beaker and draw our ions in solution. Or all of our species in solution. I should always say species in solution, and that's I2 not IS. We have our Mg2 plus and we have our I minus. So let's add some silver nitrate to it. The silver ions are going to split from the nitrate ions. And then the silver is going to attack that iodide and form a solid. That will form a precipitate, which will remove the I minus from the solution. That's how the uncommon ion effect works. It removes an ion from the solution, which pulls the equilibrium to the same side. The uncommon ion effect removing an ion that pulls the equilibrium. This is the second really important sentence, so important that I'm going to highlight it. One last thing about equilibrium is that the equilibrium constant is dependent upon temperature. Some equilibrium might have a large equilibrium constant at a particular temperature, but that same equilibrium could have a different constant at another temperature. So often on homeworks and exams, at least when I was a student, we would be given an equilibrium constant to do some calculations with, and they would give us the temperature as well. But they're giving you the temperature just to state that it's the equilibrium constant at that temperature. You don't actually have to involve the temperature in your calculations. It's just a detail to look out for. So we're going to treat heat as if it's a reactant or a product, and just put it on that side of the equation. So if heat is a reactant, if you have to add heat, then the process is called endothermic. And if heat is a product, then we call it exothermic. And we just treat heat as if it was a common ion. It works the same as the common ion effect. You can add heat or remove heat. I guess I should say, to be clear, it's like any of the ion effects. If you add it, it's similar to the common ion effect, pushing the equilibrium to the opposite side. And it also acts with the uncommon ion effect. When you remove heat, you're pulling the equilibrium to the same side. So let's look at this example. It's got N2O4 plus heat is in equilibrium with 2 NO2s. And these are all gases. So this equilibrium is what we observe in the sky as smog. If you see a really smoggy city, Los Angeles used to be this way before the Clean Air Act, and it is sometimes still, but it's a lot better than it was. During the summer, you'll see this nice brown haze, very nice brown haze. And that is NO2 in the atmosphere. This is the same gas that you produced in the copper cycle reaction, in that first reaction, the supertoxic gas. That's NO2. That's what you're breathing in the summer in a large city. But in the winter, you don't see it. Does that mean that the pollution just goes away? No, it just gets converted to N2O4, which is colorless. During the summer, you add heat, you're pushing the equilibrium to the opposite side. And so you have more NO2 in the system. And when winter comes along, you're removing heat, pulling it to the same side, to N2O4, which is colorless. So the take-home message of that is you're breathing in toxic chemicals either way. Sorry to end on that cheerful note, but this is the last lab of this semester. This one can be a challenging lab, but the tip I have to offer you is always draw your species in solution. Always draw your species in solution. If you're wondering what's happening, draw your species in solution and ask yourself, who is soluble with whom? Review your solubility rules. It's only by the solubility rules that we know that Ag plus and I minus will come together to form a solid. We need to be able to recognize that in our solutions. And as always, please don't hesitate to send me an email. If you are ever confused, even if you have already drawn your species in solution, just send me an email. We can talk about it. We can have a meeting over Zoom. Whatever you need, I'm here to help.